Oh, it's okay. I'll just leave it. I'll leave it there. Let me just pray for a minute. Dear Father, we again thank you for this day, and I just ask you to just bless this time that remains as we talk about the quiz. Lord, in your name I pray. Amen. Okay, so the quiz, the solution is here. All right, so let's talk about it. So to prove that A plus B transpose is A transpose plus B transpose, we just look at the ijth component and appeal to the definition of transpose, matrix addition, and then the same. And since we can prove it for all ij, that suffices to prove that the identity is true. Yes?
Is this online?
No, it's not online yet. But I will.
Okay, it will be?
It will be, yeah, eventually.
That's what I meant, sorry.
It's okay. I mean, in the abstract, yes, because we're looking at it here, which means I sent it through the internet. But in the way you're asking the question, no, not yet, because I'm running around like a chicken with my head cut off today. So it's all Dr. Sprano's fault. He apparently had to go to the dentist or something. I don't know. I'm teaching 6 classes today. It's very exciting. So it's a personal record. Personal record. So anyway, here we have 2 equations and 2 equations and how many unknowns? 3 unknowns in Z7. So I did row reduction to get to that. And that tells me that x plus y is 3 and z is minus 4, which is equal to 3. So the solution set is 3 minus y, y3. And of course, y being a free variable means the cardinality here is 7. There are 7 solutions in this case. 3 is the is all about the CCP. So by this column correspondence property, I can see that A, which is this column, corresponding to that column, is the first column plus twice the second column. In other words, A is equal to V1 plus 2V2. And B, well, B is the 5th column, and I can see that's 3 times V1 plus 4 times V2 by direct inspection of the reduced echelon form. So these are apparent by the column correspondence property, and then if you put those together, A plus 2B is this, which is in the span. So yes, A plus 2B is in the span. No. No. Why? Because I decided to just ask for no because the way you guys explained it last year, it was so depressing for me to read. I decided I didn't want any part of it. So I just want to know there. They don't pay me enough to read your explanations for the no. And so anyway, just kidding. C, mostly. C is the last column. As you can see, there's no way to build the last column from the previous 5, which means that C is not in the span of V1, V2, V3. All right. Problem 4. Why is my computer not charging? Huh. I mean, I have it plugged in. Yes, see this plug, it's a trap.
I have a question.
Yes.
On one that you did.
Yep.
On number 2, it said C is equal to -4 is equal to 3.
Add 7. It's mod 7, so like -4 plus 7. It's the same congruence class. I should put bars on everything, but if I don't do it, you don't have to do it, right? So you'd rather not have to put bars on that kind of problem. Okay, so this one here, find the equation in ABC which places ABC in this span. Well, if we think about this, this means that ABC would be linearly dependent on V1 and V2, labeling these V1 and V2. So that would mean that this matrix has to have determinant 0. Otherwise, it would be, you know, the case that these columns were linearly independent, of course, which we don't want that, right? So I put the determinant equal to 0, and that gives me the condition that I want. There are, of course, more complicated ways to try to do this, which is why you ran out of time. my most patriotic and or politically charged linear algebra quiz ever.
Oh.
Okay. Sorry. You dare me not to? Yeah.
Show it to Jerry.
Yeah.
Now
Now, so listen, you guys, you did horrible things on the homework. The bananas problem, like you're just commuting the matrices like mad. You can't do that. Matrices do not commute unless you're told that they do. So you must take care to multiply on the left versus multiplying on the right. These are inequivalent. You can't just multiply. You have to multiply on the right or multiply on the left. It matters because matrices don't commute. So anyway, I wanted to put that on the quiz because I didn't have a chance to emphasize that until now. Problem 6 should be fairly cut and dried. Row reduction, row reduction, row reduction, row reduction. I got that. Did you guys get that? Okay. It's good because I just did this calculation today, which makes me very suspicious of it. So I'm happy you got the same thing. So at least we're both wrong together. No, we're right. We're right. So the first row tells me that x1 is that. The second row tells me that x2 is that. The third row tells me that x3 is that. Notice that I put the variables on the other side, and so doing swap the signs. Like plus 4x turns into a minus 4x4. Plus 8x4 turns into a minus 8x4 when I put it on the other side of the equation. And likewise for those terms. So here, the non-pivotal variables x4, x5 appear as parameters in the solution set, right? If this also was over, a finite field, there would be, if it was over a z mod p, there would be p squared worth of solutions in this one. If this was like over z7, there'd be 49 solutions in this solution set. But here, if I had asked about the cardinality, there would have been an infinite number of solutions. Now, I hope you realized, maybe you didn't, I tend to do this sort of thing on tests. If I have a problem and then another problem on the same page, be on the lookout for the numbers being the same, because sometimes I try to simplify your life by, look at this. So this is the matrix with the identity. So you did the row reduction, now you've got the identity, and that's the inverse of that matrix. So that's the inverse. And there you go, that's V. Now, if you try to solve this directly, well, it's not that bad. I mean, you have these 4 row reductions to go through, but you should have had a strong sense of déjà vu as you were doing that. Yeah. When I put this on the test before, I had one student who gets like all the way through the second row reduction, doing the same thing over again. And they're like, and then they write, ah, I see it now. It's like, I know. I know exactly what happened. So do take a second to think before you just mindlessly calculate. I do try to build in things that allow you to simplify the calculation on the test. And there's usually these sorts of things on my tests. Yeah. Calculational techniques are there to use when they're appropriate, but sometimes we fall back to the definition, right? Like this problem we had in the last homework. Was it mission 2? Like problem 25, right? I mean, sometimes it's not, if you tried to approach this by just putting it in a matrix and row reducing it, you wouldn't have been able to do anything. Because I haven't actually told you what V1, V2, and V3, and V4 are, except to know that when you multiply on A, you get these various quantities. So yes, row reduction of the super-augmented matrix by the identity is a nice way to calculate the inverse. But you should be aware there are other ways of approaching it. What was missing from my quiz, which might be on the test? That's probably good to talk about. The E matrices. And we could take that either way, the EIJ or the elementary matrices. Both would both be good comments, because I usually do test on elementary matrices. I usually test a little bit more on the EIJ, like the standard basis stuff like, what's A times EI? This is what? Column, the ith column of A. What's EI transpose times A? The ith row of A, right? What if I have EI transpose times A times EJ? What's that? Exactly, that is Aij. That's the ijth component of A. So those things I do want you to know. How to build a matrix from the matrix units. The other thing that didn't appear and almost appeared is a question about symmetric versus anti-symmetric matrices, or something about nilpotence. I often, or diagonal. These things I will at times test on.
Have you written the test yet? Or are you like Dr. Sprano?
What does Dr. Sprano do?
He waits till like 3 a.m.
when our test is at noon.
Oh, okay, that seems reasonable. Is there something that confuses you?
Don't say it.
Matrix addition is very confusing.
Yeah.
Matrix addition.
Yeah.
Especially
Good.
matrix by constant.
That is something that's missing from this quiz, matrix multiplication, right? Matrix multiplication is important. Well, it's sort of in this. Determinants? Yeah, well, determinants was hidden in problem whatever.
Can you not put a lot of those?
I think
Those
that's
are
hard.
really confusing.
Okay. I got it, yes.
So, I missed last.
I was mostly confused because I didn't know what the those was referring to, but then I understood.
Determinants
Yeah.
are hard.
The determinants are hard, yes.
I missed last class, so when I was watching the lecture video, you're talking about the eigenvalues near the end of it.
Uh-huh.
Like, is that something like you were just briefly mentioning before this test, or will that like something that's going to be expanded upon later, not necessarily have to worry about right now? Or like if it's going to be on the test one day, can you like go over it a little bit?
Well, I mean, I would say that the eigenvector concept, if it was tested on, it would be tested on in a similar way to the way it was discussed in class. So it's unlikely I ask a computational question about it. That's kind of an acquired skill, actually calculating the eigenvalues for a given matrix. But it's not an unreasonable question. I mean, here's an example.
Right, like I just wanted it clear. I just wanted it to be clear. I did not quite understand.
Where A equals whatever, right? So how would you solve that? It's pretty simple. If that inverse doesn't exist, that means the determinant of A minus lambda I has to be equal to 0. So if I give you a particular matrix, say, I don't know, 0, 3, 0, 6, 7, 0, 0, 0, 8, I don't know, then the determinant of A minus lambda I is the determinant of minus lambda 3, 0, 6, 7 minus lambda 0, 0, 0, 8 minus lambda. And you have to work that out. So, I mean, the reason that's a kind of a nice question is it kills two birds with one stone, in the sense that it tests you guys on your understanding of invertibility. What does it take for a matrix to be invertible? And at the same time, it's a determinant calculation. So it's kind of a twofer, which makes it a nice question. But traditionally, I haven't asked it, but it's not really outside the realm of possibilities.
Just out of curiosity, why is it only the diagonal entries that give the eigenvalues in the determinant calculation?
So this one, just 1 second here. This is, you notice 8 minus lambda factors out?
Right.
So that's lambda times lambda minus 7 minus 18. So you could actually find the eigenvalues as they're known for this matrix. It wouldn't be that bad. One of them's 8. Yep.
Are we going to be tested on wedge products?
No.
What are wedge products?
What are wedge products?
Yes.
Videos that talk about wedge products
It's
are
the
your videos.
videos.
Are you trying to artificially inflate your views?
Are you trying to find it in Khan Academy or something? I mean,
I'm trying to find it anywhere.
Anyway.
On the black market.
you think I just made up wedge products? Yeah, they're.
I think that actually is.
I invented wedge products. They're all mine. No one else knows about them. Yes. No.
Well, we're
Is a lie.
going to be teaching it later.
Or at all.
Or, okay, Bethany Matzik still doesn't understand wedge products, so I don't think anybody in this class will ever understand. Thanks. To be very intelligent. Well, yeah. If Bethany doesn't understand it, I don't think anybody will. Thanks, Bethany.
I don't think that's an allowed method of argumentation.
And here's the plug for advanced calculus next semester.
Yeah, for real.
Look. Wedge products are a new thing. I mean, E1 wedge E2, it's not a vector. It's a new object. It's a 2 vector. E1 wedge E2 wedge E3 is these are not even the same type of objects. This is just different than that. But what makes them interesting is their algebraic properties that I had in your homework problems. They're a way of building determinants from an algebraic system. Now you might say, what are they? Well, you could formalize it. You could build matrices which behave as these. And so, I mean, what's a complex number? See, some people would say a complex number is a 2 by 2 matrix that looks like this. Because 2 by 2 matrices like that behave as complex numbers. You can add them, you get matrices of the same type. You can multiply them, you get matrices of the same type. The matrix 0, minus 1, 1, 0 squares to minus the identity matrix. In the same way, you could build sets of matrices which behave as the wedge products. So you could find a concrete realization of them. Pragmatically speaking, though, what the homework was about was just exploring wedge products, like just their basic algebraic properties. It's a way of testing linear independence of just a finite set of vectors. If the wedge product of vectors is 0, that means there's a linear dependence amongst them. I can only test for linear independence with a determinant if I have n vectors in an n-dimensional space. In contrast with wedge products, if I have 2, if the wedge product of 2 vectors is 0, they're linearly dependent. If the wedge product of 3 vectors is 0, they're linearly dependent. If the wedge product of 4 vectors is 0, they're linearly dependent. So it's a much more robust way of looking at linear independence as a direct calculation. But it comes at the cost of weirding you guys out, right? If you want a better answer, wedge products are the algebra that's behind differential forms. Differential forms are the way we do calculus on curved spaces. Vector fields really are only good for 3 dimensions. Past that, differential forms, and vector fields, but I'll shut up. All right. Anyway, I should have your quiz 1 graded. You can pick it up